Okay, so today's webinar is titled Measuring Real-World TIM Performance with a TIM Tester in according to ASTM D5470 standard as a part of our educational series from C-Therm and partnerships with ZFW Stuttgart. So, you know, going right away in a world where of high performance computing and complex battery packaging, thermal interface materials, and any thermal management system really are have becoming more key in dictating overall safety and overall performance as a whole. So in this context, if you look at it, a thermal interface material is only microns thick, but it can decide whether the product as a whole runs, fails, or burn down. So it's a bit extreme to really look at it that way, but with high computing power requiring to generate so much of the heat, we'll need something to really mitigate all those issues down the road. So data sheets really overall values rarely reflect real assembly conditions. So contact resistance, pressure, bond line thickness, pump out effect, and agings are often the final dictator of thermal performance of the material. So if you don't test the interface, you're not really testing the thermal pad. So most thermal failures don't really start at the heat sink. It starts at that interface. So it's really important to understand the performance of your TIMs or any of that interface material as a whole to better understand your assembly. So starting with the basic definitions for the whole of this session. We'll start with the TIMs, so TIM. Thermal interface materials, or TIMs, play a critical role in moving heat from the heat source, in this case highlighted in red, into, let's say, a heat sink. And although the die or something like a die or a heat sink are relatively flat at cross microscopic level, there is actually in reality there is like air gaps and peaks and valleys in there that really creates a significant thermal resistance to the heat flow. So TIMs are specifically designed to fill this contact between the two surface. And in a day of age where power densities really continue to increase across applications such as AI, high performance computing in data centers, aerospace, power electronics, we're often seeing limitations where the overall system have issues cooling down. So understanding and accurately measuring TIM, thermal resistance, and thermal impedance is therefore essential for optimizing thermal management and ensuring reliable device operation. So, there are many types of TIMs that exist nowadays, and commercially and in the R&D level. They can come in many forms, each designed to meet different thermal, mechanical, and even manufacturing requirements. So, common TIMs involves a gap pads, adhesives and paste, thermal greases, phase change materials, gels, and disposable compounds, or even nowadays with like high performing liquid metals, right? So while all TIMs serves the same purpose as a whole of reducing thermal contact resistance, their performance can really vary depending on the application conditions, bond line thickness, pressure, and all that mentioned earlier. So selecting the right TIM requires the balance between that thermal performance and the actual conditional parameters involved. So, you need to have that reliability, ease assembly, long-term durability to take into account. So in this webinar, we'll explore how these different TIM technologies are evaluated and compared using standardized testing methods. So TIM testers as a whole supports testing conductivity and also other different properties. right? So modern TIM testers really provides you that insight into a whole range of performance characteristics that impacts real-world performance. These systems can evaluate thermal impedance, contact resistance, delamination effects, curing performance, bond line thickness, and thermal and mechanical aging. I will be talking about specific examples directly pertaining to these parameters. Um, but the message should be is that like ultimately measurements of these parameters provide critical informations that goes well beyond what is typically reported on a material data sheets. So you can see here, there's different images of like, there's going to be a difference between what you'll get on a TIMS as dispense versus TIMS under operational conditions, especially with aging into context there. All right, so before we'd like to really dig deep into the details here, I'd like to start with a polling question here. So what type of TIMs are you working with? So, I'd give everybody a bit of a few seconds here before I'd end the poll. And, feel free to add any details also if the TIMs that you guys are working with are not within the list. So, we'll have a little bit of a chat in there and how would you fit your material into our testing capabilities. And I think that's it. Okay, I'll be sharing the results now. And it's interesting that, thermal paste and thermal adhesives really dominate the field here. And of course, we see that thermal tapes and films are kind of like second common into the results there. Thinner the materials, more high performing. That's really where the general directions of developing the new generations of TIMs. What's really interesting here are the other, non-mentioned options, and would like to know more about it if you don't mind. All right. So moving on with our next slide here. So in general, this webinar will be split into basically uh, four main components. So you can see like explaining the basics of principles of the TIM testers and how the instrument basically perform accordingly to those principles. And then I think what everybody will be excited about would be, specific applications and use cases, including very kind of like, I would say, niche applications that are seldom seen in a commercial setting, but more on like, very, very specific in a high performance type cases. And of course, would like to very quickly maybe go over some extended capability that is available specifically for our TIM tester that we use in-house and our partner ZFW that may offer some insights and also maybe some opportunities for you guys to test your maybe you have much more complex systems in there. And at the end of this session, we'll dedicate some time for some Q&A. Okay, so starting with the measurement principle, and I'd like to go over it as quick as possible, and I'm assuming some are familiar, but let us know if you'd like to get more details down the road on how exactly the math works out and all of that. So, as mentioned earlier, the TIM tester works in according to these D5470 ASTM standard, specifically again describing the TIM tester as each of the process and the method required for it. So what it does, what it covers is the measured quantities is that you have your thermal resistance and impedance denoted as R for this session under the millimeter squared Kelvin per watt units. And of course, our apparent and bulk thermal conductivity, again, denoted as K, and watts per meter Kelvin units. Specific thermal contact resistance, which can be very important in certain applications, denoted as RC, again, the same unit as the thermal resistance up here. This typically are split between different types of material classes. So you have your liquids, your water, oil, thermal greases, um, viscoelastic solids. So you're talking about polymers, pads, gap fillers, foams, and of course, elastic solids are a bit more stiff, relatively speaking, or less viscous when compared to the other materials mentioned. So you're looking at your thermosets, rubber, ceramics, metals. And as the general configuration for the setup, you're looking at in this here, where your sample is going to be sandwiched between two test bars, so upper and the lower meter bar right here. Typically, you'll have your heat source on the top, simulating all that, the heat sources and your CPUs, GPUs, or data set, all that heat sources. And you have your lower bar, which simulates your heat sink in general, and then your samples in the middle. And the general idea there is that you have thermocouples attached at different position in the bar, and from the top and the bottom, in this case, we have four, and then you generate the temperature gradient in there, and then you'll have all this different temperature points and generate that slope. So based on this, you'll have your heat flux essentially. And then knowing what the delta T and the thickness, you'll be able to calculate different values from it. So for example, thermal conductivity in this case is a function of the heat flux divided by the delta T and the thickness. And your resistance is going to be the function of that delta T divided by your heat flux. So very, very straightforward, no real complexity when it comes to the math. It really comes to the accuracy when it comes to that is like your measurement points and how accurate your hardware and software at the end of the day. So another kind of like breakdown right here would be at the end of the day, the direct output of the method itself is going to be looking at resistances, and that resistance or total resistance involves the bulk resistance of the material itself and the contact resistance between the material and the interface, which is typically the bar right here. The bulk or the total resistance as a whole can be broken down into two components, the bulk resistance and of course the total contact resistance from both surfaces. At the end of the day, when we're looking at this thermal impedance R, which again is made up of this bulk and contact resistance, you'll get apparent thermal conductivity. And apparent is very important to really note here, is that it indicates the inclusion of contact resistance in the math. To be able to get the bulk thermal conductivity, we will need to measure the bulk resistance and remove the contact resistance effect on the measurements. And how do we do that? So it's pretty simple, really. It's pretty straightforward. To distinguish the bulk thermal resistance from the contact resistance, we need to perform a bunch of measurements that involves multiple bond line thicknesses. So in this example right here, we're looking at the grease, measuring the specific thermal resistance R, and measured across different thicknesses, right? And what you get here is basically a linear regression where the slope is a very much indicative of the bulk thermal conductivity, and the y-intercept is the contact resistance, or two times RC in this case. So you can see that the final value here is that the bulk conductivity is 3.15, while the 2RC is 4.9 millimeter squared Kelvin per watt. And there are different ways and inputs that we can control when it comes to measurements. You're measuring conductivity as a function of either thickness or gap or pressure control. So you either control the pressure, you either control the thickness. So there are two ways to do that. So the same materials can have different outputs. In this case, you can see, you measure specific thicknesses. So this is where you control the gap. or you control the pressure itself. So you can see that the behavior is a little bit of a variable across the board. And this is the conductivity, and this is the resistance versus the pressure applied and from different uh, utility. And there's going to be uncertainty involved in this specific method as a whole. What you're seeing here is that, as I said, the direct output is resistance, and there's going to be limits, lower limits and upper limits when it comes to that when you measure it. So resistance is a function of delta T and the heat flux. So having a small delta T or in a range where delta T is going to be small. So for let's say highly conductive materials with low resistance, meaning that delta T is low, what you'll see is that you're looking at the at some you're reaching that lower limits as a whole. However, the other end of that is that to compensate for that sometimes is that you have to increase the heat flux Q right here. But then if the flux is not controlled properly, if you're reaching a point where you're having more heat loss than the flow, you'll have increased uncertainty also from there. Okay, so that is the basic principles of it. I'm going to go over the instrument itself that we use coming from ZFW right here. But before I go over, I'm going to quickly mention that, who we are and why we do what we do. So we are C-Therm Technologies. We focus a lot on transient methods. For the most part, we're considered ourselves our world leaders in thermal conductivity and specializing in non-destructive thermal analysis solutions. But as kind of like context-wise for this webinar, we'll be focusing on the steady state technique to tin tester. And speaking of steady states, we're also capable or have the capability to measure two different type of steady states, and in this case, the TIM tester we'll covering today, but also the high temperature heat flow meter, if that is something of interest for you guys. So if you guys want to learn more, the QR code is available for access right there. Okay, so very quickly here, this is the TIM tester itself. So you can see here, you have your measuring chamber. The TIM tester itself is inside this chamber. You have your PC, the base frame, and the control cabinet. So relatively speaking, right away, you'll notice that it is a large instrument, right? Comparably speaking, compared to the other TIM tester in the market out there, and that has a certain merits on itself. It maybe space is very important to you, that's something to account for, but having a large thermal mass is actually an advantage to a certain extent, because that really translates to, overall lower sources of error when it comes to, let's say, heat losses, right? Okay, this is going to be a close-up view of the testing stack itself. So you can see here that you have the upper and the lower bar, the heat flow or the heat source and the heat sink, and you notice that there's this two components right here. These are an optical keyings, a cam LED optical camera, which is unique in terms of the ZFW TIM tester. And this is how we measure the bond line thicknesses in a very accurate manner. And I'll showcase why we went for the optical way and not the usual physical manual way. And you can see this is just another view of you have the hand pump right here to control the up and down, and the fine-tuned control is controlled by a electronic rotor or motor. Okay, so thermal design wise, we have all this spec mentioned right here. So you can see that, we're looking at very much, within the boundary conditions of application-specific cases. There is a plane parallel surfaces where the upper is actually you can lock or unlock it so that it can adjust to any type of scenario in case your surfaces are not flat. The diameter of the testing is about 30 millimeter. This is adjustable if that is something that interest. The temperature on the upper bar can go up to 175, while the heat sink, which is fuel fluid cooled, can go down to 5 degrees Celsius, and even lower. It really depends on the dew point of your environment, and that translates to about a mean temperature, which is your sample right here, about 10 to 150 degrees Celsius. And very much so that there you have your thermocouples with very, very small diameter, 0.35 millimeter, which really translates to really high accuracy, very, very much good contact with the bar, and you have no air sources when it comes to your final temperature detection when it that. Some geometrical consideration here. So I mentioned that there is that Keon's IR camera at the beginning. So this, what it does is that it measures the shadow between these two bars from the this protruding bar right here, and that way you can measure the your gap with your sample right here. So you tear it, and then you'd zero it, and it's all about relative measurements. And what it does is that you eliminate two main sources of error from there, right? One of them is that you have parasitic heat loss path in that sense. So if you have more components touching the whole overall stack, you'll have more ways to lose heat through conduction, essentially. And more importantly, I think that is very much so is that you have to take into account thermal expansion as a whole. So if you're heating and up the whole system, the bars will expand, everything will expand. So by using that non-contact capability, you'll minimize all of that errors. And I think it gets really important when it comes to really, really small micron range and high performance, high K, low resistance type of measurements, right? And again, I mentioned there's some mechanical designs right here. You have the top mount is floating, so that way you can adjust to the parallelism available with the sample. You have the lifts and surface pressure of up to 2 newtons per millimeter squared. That translates to about 290 psi. And you'll have some automated capabilities when it comes to going up and down, and especially control. Very quickly, this is pretty much what the UI would look like. You can see that your outputs measured gap from the Keyence camera. You have your measured surface pressure during the test itself, and you have your apparent thermal conductivity and the impedance also shown in that portion right there. This is your the temperature control, and this is pretty much the current state of your steady state status. And in addition to that, you can also customize test runs, cyclical, or if you have a very specific steps profile that you'd like to use, that is pretty much available for that. So depending on your application. And of course, there's going to be the report at the end of the day. So you'll see that, once measurements are done, what kind of data would it look like? You have your raw data and also your graph showing up right there. Okay, so that's pretty much the overview of the instrument. So I would like to go over some of, another quick poll right here. How are you currently testing your TIMs? Is it through some steady state, or is it through any other methods? So if we could have the questionnaire up, having some slight delay here. It's not showing from my screen. So just by the way, if you have any more questions, I have Carter here helping me mod this webinar. Um, it seems like the poll is not appearing as it should be. Um, okay, well, uh, we'll move on from here. Sorry about that. If you'd like to leave us any comments at the end, or maybe mention it at the Q&A session at the bit, we'll go from there. Okay, so now I'm going to be going through some application cases or applications and use cases that have been done using the ZFW TIM tester. And I'd hope that some of these cases are very relevant to your work, your applications in general. So first thing is the tracking the curing of a thermal gap filler. So some of these gap fillers, like maybe adhesives or uh, if you have to cure it for during the applications, it is possible to cure it directly to the TIM tester itself. The advantage of that is that you can actually track the thermal properties from non-cured and during curing and then post-curing, right? So you have that continuous measurement. The downside of that is that you're actually um, it's a quasi steady state at that point because things are moving around. It's the heat flux itself would be, it's not really steady state in a very technical manner, but what you're getting is that direct output of that transient condition, right? So you'll have relative evaluation of your resistance as that is ongoing. And you can control that as a function of constant pressure or constant gap. So you can see there's different properties as a function of that gap with the same tips. Highly conductive thin film TIMs. So we're talking about graphene and graphites, maybe in this specific example right here, or even like some metal foils. In this case, you can see that there are different graphites with different thicknesses. And some of them are most likely going to be pyrolytic. Some of them are uh, expanded foils, but it is possible to measure their through plane thermal properties. In this case, we're showcasing the thermal impedance in the Z direction um, and at different pressure. So you can see here that we can what's really important to note here is that it is possible to actually reach or measure very low um, thermal impedance. So zero point 0.9 millimeter squared Kelvin per watt is very low when it comes to that. I believe, depending on the thickness, in this case, 0.1 millimeter here, that could translate to some high. I can't do it on top of my head, but that is very high performance graphite right there. And another one that are really upcoming nowadays is liquid TIMs. So you'll have liquid metal interfaces here. So the challenge here is actually not measuring itself. Well, that is part of the challenge, but it's the chemical compatibility with the bars that are being used. So more often than not, there has to be some sort of customization that needs to happen where you need to change the bar that you use to directly contact the liquid metal itself. So it's typically gallium or indium or iridium based alloys, and they typically are well known to really corrode aluminum, which is what the standard TIM tester is usually made of, or sometimes copper. So we need to make sure that there is some chemical compatibility happening right here. But you can see here that it is possible to measure it using the TIM tester. Just need to really take into account that compatibility issues. And in relation to that, there is some, we can change the types of bars that we use, but also we can also use this what we call the substrate disk, right? So they're more of like a quote unquote, a sacrificial disk or an extra disk to kind of like interface between the bars and the liquid metal itself. Also, we can directly control the quality on the polish of the surface quality of the disc itself. So you can have like matte or mirror finish. And that has the direct implications on the thermal properties, especially the contact resistance of the temps. Uh, Here is an example of gap width elongation testing when it comes to the gap filler. So what it is that like you have your gap filler right there, and what it does is that it imitates what happens when that gap between the heat source and the heat sink expands during high temperature applications, right? Because everything will expand, including the surfaces itself, and that has direct implications on the performance of your temps. So, you can control, like, let's say, I want to have a gradual increase of 5 micron every set time and avoid any delamination effects right there. And you just want to understand the change on the properties itself. So, we can investigate, time dependent effects, some creep, some relaxation. You can even go the opposite way where things, instead of expanding, things are, you know, getting smaller. And of course, the classic delamination testing under a cyclic condition. So you can have the bars go up and down in a very specific frequency and a very specific, time range, and define that at how far you'd have to expand it. And this really kind of like imitates long-term use where, yeah, maybe in your system you have a lot of vibration involves, or you just want to see kind of like a aging type scenario where eventually you'll see some physical change in the temps due to the change in the hot cold kind of like changed maybe during winters and then summers. You'll see that, and you can see what kind of like a worst case scenario you should expect. So you can have the lamination effects right there, and you can see that the significant change when there is the lamination happening. And you have the uh, performance versus temperature itself. That is also possible. Um, the In this case, there are so many parameters that we are controlling, but we want to maintain the same condition. So in this case, you want to maintain, let's say, the same gap every time, right? No matter what. And across different temperature, what does it look like? And then, you can control what that mean gap temperature would be from there. And thermal aging, very classical that way with different thicknesses. You can see how different, what happens at eventually, exposing it to a very set temperature at a very set amount of time, and then what changes to the physical and the thermal properties from there. So, very classic in this case, especially with adhesives, TIMs. And of course, compression, long-term compression can have that really drastic change into the properties itself. So you can see that, when you press the material, there's going to be some relaxation involved, but then some irreversible compression, probably, depending on your material. But then, you'll see what happens at compression at specific temperature. So you can see in this TIMS that there is a gradual increase in resistance or decreased in this case at room temperature, but at high temperature you can see that there is an increase in resistance, which tells us that there is a drastic change in its physical and thermal pathways from there on. Okay, I'm hoping that calling is working at this point. Very quickly, maybe we can have a uh, just there you go. So, um, you know, questions of like what type of measurements are you most interested based on our mentioned so far? Like what kind of properties, maybe what type of studies specifically, or maybe you have your own specific interest that you'd like to see. So let us know, um, and you know we'll give everybody a few seconds right here. That's interesting. Yeah, very very wide distribution. So we'll give it another couple seconds here. And all right, so I'm just going to end the poll over here and share the results. So you can see that thermal conductivity really dominates the what most people would like to see, and again that the TIM tester calculates the conductivity based on the resistance and the measured thickness, and having those accuracy for both measurements of resistance and measurements of thickness it has direct impact on how accurate you can get for thermal conductivity. And you can see here, curing and aging studies and even bond line thickness are another kind of like most what people would like to see. So thank you for sharing, and I guess we'll just move on for the last portion of this session. So the last thing I'd like to mention before we go to our Q&A is, the extended capability. And this one is a bit more specialized in very specific applications. And, again, getting ahead of the curve where we're seeing more advanced requirements when it comes to testing, because we're seeing a more advanced type of materials is pretty much what innovation is all about. So you can see here what we call the micro-thermography, again, very much developed by ZFW right here. And if you'd like to know more about it, there is a QR code right here on the published paper about how this one exactly works. So what you can see here, there is a specialized add-ons to it. So very specifically, this high-performing IR camera. And what it does is that it images the material, TIM material right here that, more often than not, what you're seeing is, if you're looking at multi-layer complex composites, right? And if you want to understand, let's say, contact resistance between inner layers, um, that this would be the method that I'd be recommending in a sense. You can see here, you can see that you have multiple layers with the substrate, and you have fillers within the material itself. So you can see that this is the mapped out thermal resistance or thermal impedance across the z-axis as mapped out by the thermography right there. And you can see that there's different, slopes that are basically indicative of the contact resistances and whatnot, and filler effects within the substrate itself. So, you can see that, in a clean, let's say epoxy unfilled, you can see that there's that the behavior on the resistance right here are different, right? So you'll have a different slope, which is indicative of, the contact resistance, and then you have your epoxy slope right here, um, which is in the 4,000s essentially, or in the 1,000 range. And again, contact resistance over there. But then if you have, let's say, alumina fillers involved, you can see that the scale is actually a lot lower, and then you see that the thermal behavior is a lot different compared to the one without any filler. So that's just one layer, and then you can have multiple layers, and it's possible to really map out each of those layers from there on. So if you have special applications or composites and you need to understand the performance in such a way, feel free to contact us with the thermography. And of course, you'll have combinations of both. You'll have let's say uh, so you'll have adhesives, maybe solders, and center paste and all that. All of that maybe can be like you'll have multiple systems with thin layers in each of them, and you can see here that there's the copper and that and all that paste. Each of them will have different contribution to the overall property. So if you only measure this with a classical TIM tester, you'll have a different value because it's evaluating the whole average. But then if you, let's say, get a microthermography, it is possible to really capture each of that small components from there. And that's pretty much it. I'd like to go over some summary before, at the end bit here. So, you have the TIM tester from the ZFW that I've just talked about. We've talked about thermal impedance, how to measure them, thermal conductivity, and contact resistances. It's possible to really go over in a wide variety of TIMs, liquids, greases, paste, even, elastic and viscoelastic materials. We could go over 30 millimeter diameter and all that other specs. And of course, if you're interested with accelerated aging, for example, what we have here is that another special instrument that are specifically more niche in a very different direction. So, for example, there's the VT vibrational tester that is more focused on vibration itself. So you have like high frequency vibration, high energy applications. So let's say aerospace or rockets that vibrates a lot. You can see that how your properties change accordingly to those conditions. And there's this accelerated for thermal cycling. So long hour exposures maybe is very much uh, yeah. So that's these are two different platforms that are kind of like an extension of the TIM tester itself. And of course, for our own, us in here in C-Therm, I'm the lab manager for our testing lab, TAL right here. We offer different testing services using different capabilities, including the TIM tester itself. And if you'd like to know more, please feel free to access the QR code. And from here on, we'll stop the recording and we'll open up the floor for any questions.